Chapter 4.4, the Fundamental Theorem of Calculus. Day 1, the Fundamental Theorem of Calculus. If we take a look at what we've talked about so far, we've talked about differentiation, which is change in y over change in x. We take a look at what that means. We're taking our secant line, and it's becoming a tangent line as delta x approaches 0. That's differentiation. If you look at integration, we're looking at the area under delta x, delta y. And this time, areas multiplying delta y times delta x. We can see that there seems to be kind of an inverse relationship. So there's a definite relationship between integration and differentiation. And that's where the fundamental theorem of calculus comes together. It ties the integration and differentiation together in the fact that they're inverse operations. The fundamental theorem of calculus says if we have a definite integral of f of x from a to b with respect to x, we can calculate that by finding f of b minus f of a, where f, capital F, is the antiderivative of lowercase f, or f of x is the derivative of capital F of x. Saying the same thing, just in an inverse way. So how do we use this? How does this help us find the area underneath the curve? Which is what the whole idea of integration is. Well, providing you can find the antiderivative, and it's not always possible, we can now evaluate it. To find the antiderivative, or the definite integral, we'll start by finding the antiderivative from a to b, and then plug in b, plug in a, and subtract the difference. So for example, the antiderivative of x cubed from 1 to 3, we'll first find the antiderivative of x cubed. Then we'll plug in 3 and 1 and subtract to find the difference. Now, keep in mind this is a definite integral. For indefinite integrals, we've had to deal with a constant. And you can continue to deal with a constant if you want. If you take a look at what happens, we have c minus c. The constant ends up falling off. So for a definite integral, you may forget about the constant. And there will be no consequences. So it is encouraged not to use a constant for a definite integral, but it's very important to keep it for an indefinite. Let's do a few examples. Find the area of the region bounded by y equals 2x squared minus 3x plus 2 from 0 to 2. Well, first off, we can do our infinite rectangles, our definite integral from 0 to 2, 2x squared minus 3x plus 2. Those are our infinite rectangles, and our shortcut, the fundamental theorem of calculus, says we take the antiderivative of what's inside. So that would be 2/3 x cubed minus 3/2 x squared plus 2x from 0 to 2. I like to group that. And then we'll plug in 2. We get 2/3 of 8 minus 3/2 of 4 plus 4 minus, if we stick in 0, we get 0. So 2/3 of 8 is 16/3 minus 12/2 plus 4 is 16/3 minus 6 plus 4 is minus 2, which you can leave it like that, or minus 6 is 10/3. So there, using the fundamental theorem of calculus, is the shortcut for summing up all of these infinite rectangles we've been building recently. So we now no longer have to infinitely sum rectangles. We can use the fundamental theorem of calculus for our shortcut. So let's find the area under the curve 2 minus t square root of t from 0 to 2. All right, graphically, it totally really doesn't matter what it looks like. It looks something like that. Why not? What we're going to do is we're going to take the antiderivative. And then the fundamental theorem will find the area for us. We'll rewrite this as t to the 1/2. We'll distribute. We got 2t to the 1/2 minus t to the first times t to the 1/2 is t to the 3/2 with respect to t. Do our antiderivative. 1/2 becomes 3/2. Multiply by the reciprocal or divide by the fraction. We get 4/3 minus 3/2 becomes 5/2. Divide by the fraction or multiply by the reciprocal from 0 to 2. Substitute in 2, substitute in 0, we get 4/3 times 2 to the 3/2 minus 2/5 times 2 to the 5/2. If you want to simplify, you can. For me, that's good enough. That's our area underneath our curve. So you're taking the antiderivative and you're plugging in the two endpoints, your two definite boundaries. All right. Now, how can we do this on a calculator? Say we have something we're trying to find the antiderivative for and we're not ready for it. How can we use technology to help it? Well, use the integration feature in the graphing calculator. How do we find the antiderivative of the absolute value of x cubed minus 4x plus 3 from 0 to 4? I'm going to show you two different ways. The first way is by graphing it. So we'll graph the absolute value of x squared minus 4x plus 3. I'm going to start by entering that into my y1, and this is for the TI-84. So we'll graph x squared minus 4x plus 3. Make sure our window is set. I think I'll zoom to a decimal window. That usually covers what we need. Looks pretty good there. And now we want to find the antiderivative from 0 to 4. Go into the calc menu. And the calc menu is right up there. It's above the trace. So we'll do second trace. And we can see the choice for antiderivative is right there at the bottom, number 7. And it's going to say lower limit. Our lower limit is the bottom number on the integrand, so that'll be 0. I'm going to type it in. You can trace over to it and hit enter. I just like to type and hit enter. It's going to say upper limit. Again, you can arrow over to 4 and hit enter, or just hit 4 and enter. I think that's the easier way. And there it will shade it in for you and tell you the definite integral is 4. So you can graph it and use the second trace feature on your calculator. Like I said, I'm going to give you two options. The other option, you're going to go to your home page, get to a clear page, and the other option is in the math menu. Go math, and it's the 9th option. If you arrow down and take a look at 9, or you can just type the number 9, and you should get FNINT is the option. If you have the new operating system, this is what will show up. It'll actually give you the symbol. And you go ahead and you type it in. It's what you see is what you get. Here we have the lower limit. Is -2. Hit right arrow. It'll go to the upper limit, which is 2. And now we type our function. We got x times the square root of 2 minus x with respect to x. So it's math, 9th option, and then this will come up. And there it calculates it for you. Some of you may want to convert it to a fraction, some of you may not. In this case, it doesn't because it rounded. There's your value. Now, if you don't have the new operating system, what will come up is exactly what you saw when you looked at the menu, FNINT. And what you want to do is you want to type in your function, comma x, meaning with respect to x, comma, lower limit, comma, upper limit. Then hit enter, and you should get the exact same thing. The math is the same, the display is different. On the AP test, never, ever, ever write this. Always, always write something like that. All right. So, moving on. The fundamental theorem of calculus. In order to evaluate the definite integral of f of x from a to b, we're going to first find the antiderivative of f of x, symbolized by capital F of x, from a to b. Then we're going to plug in the two limits. The antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit will give us the value of the definite integral. And that is the fundamental theorem of calculus.